If you want to show that a predictor has no meaningful effect in a multiple regression, then you can use equivalence testing. In this tutorial, I will show you how to do this with R. As you probably know, it's not enough to have a non-significant regression weight in order to claim that the predictor has no influence on the dependent variable. Therefore, you use equivalence testing. In an equivalence test, you don't show that an effect is exactly zero. Instead, you try to show that an effect is so small that it is not theoretically or practically meaningful and therefore equivalent to zero. Or to use a key term of equivalence testing, that the effect is smaller than the so-called smallest effect size of interest. There are different approaches to do that. I will address two that are available within R. The first, TOST, two one-sided tests. You define an equivalence interval so that an effect size that falls into this interval is deemed to be equivalent to zero. And then you run two one-sided tests. The first test, you test whether the effect is smaller than the upper bound of this equivalence interval. And the second test, you test that the effect is larger than the lower bound of this equivalence interval. And if both are significant, you know your effect size is within this interval and thereby very small and equivalent to zero. There's a second approach that leads to exactly the same results, and that's based on a confidence interval. With this approach, you construct a 90% confidence interval. It's important, 90%, not 95%, because here we look at one-sided tests and check whether this interval lies completely within this equivalence interval, because then you have shown that the regression weight is equivalent to zero. Both approaches lead to exactly the same result, as long as they are calculated based on the same assumptions, and it's a matter of taste or convenience which one of those two you choose. Before we go to the R code, there are three important things to consider when you are doing equivalence testing. First, in general, you need a very large sample size, definitely in the hundreds. And the smaller the equivalence interval you are defining, the larger the sample size you need to show equivalence. Second, you should define the equivalence interval before looking at the data. And it's your choice whether you use unstandardized regression weights, Bs, or standardized regression weights, beta, for your equivalence test. Both is possible. If you want to know more about how to choose those equivalence intervals, or the so-called smallest effect size of interest, there are some articles by Lakens and other authors. You can find references in the video description. And third, the equivalence test is based on multiple regression, and multiple regressions have assumptions like normality, homoscedasticity, linearity, and so on. And only if those assumptions are met, then the equivalence test can lead to correct results. So you have to check those assumptions. I've made a separate video about how to check regression assumptions with R. You'll find a link in the video description. Now to the R code. For equivalence testing with regression, I use the library negligible. As an example dataset, I'll be using empty cars. That's an inbuilt dataset in R, so you can replicate the results yourself. Let's say we want to predict the miles per gallon of different cars by a number of technical properties of those cars. Let's use horsepower, cylinders, weight, and rear axle ratio. First, let's run a multiple regression. That's not strictly necessary, but I think it makes sense to first look at regression results. Since later on I will using standardized effects for the equivalence test, here I run a regression resulting in betas with using the scale function for all variables. Here are the results, and for instance, for the rear axle ratio DRAD, we have a non-significant effect. But we can conclude that this predictor is irrelevant for the miles per gallon. For that, we would need to run an equivalence test, and that's what we'll be doing. For an equivalence test, we use the negreg function, first the data frame, then the regression formula, in the same format you use in the LM function. Then you have to specify for which of the different predictors you want to perform an equivalence test. Here I want to test betas, that is standardized regression weights. For that reason I set STD to true. If you want to define your equivalence bounds in unstandardized regression measures, then you would have to set STD to false. Now to the key values, and in practice the most difficult input parameters to specify, the lower bound and the upper bound of the equivalence interval. In this case, I use minus 0.10 and plus 0.10 as equivalence boundaries. Even though there are no cutoff values by Cohen for multiple regression, for a correlation, 0.1 would indicate a small correlation. And since betas and correlations are at least somewhat related, I think one could make the case that this would be a small standardized regression weight. At first, I run it without bootstrapping and tossed two one-sided tests. The output starts with a 90% confidence interval. And we would have shown equivalence if this confidence interval had been completely within the equivalence boundaries of minus 0.10 and plus 0.10. Here that's clearly not the case. The 90% confidence interval is much wider than the equivalence interval. We get the same results also in a graphical form. In red are the boundaries, and we can clearly see the 90% confidence interval for the beta, that is for the standardized regression weight, exceeds those boundaries. So we haven't been able to show equivalence to 0. There's a very basic reason for that. As I told you earlier, you need large sample sizes in order to have a good chance to show equivalence. And in this case, we have a very small sample size in this example dataset. But I wanted to use an example dataset that is available to you as well. Next, the second approach, the two one-sided tests, tossed. Here we get the p-value and it leads to the same result. It's not significant. And at last, a so-called proportional distance. This is the proportion of the effect to the equivalence boundary. But from my point of view, this is not that interesting. As I told you earlier, this is based on regressions, and all regressions have assumptions. And if those assumptions are violated, then the regression can lead to false results, but the equivalence test as well. So normally you would have to check all regression assumptions and only run this test if those assumptions are met. But there's an alternative, at least regarding normality and homoscedasticity. You could use bootstrapping. Bootstrapping does not require normality and is also fairly robust against possible heteroscedasticity. So I use the same code with 3 changes. I change bootstrap to true, and as additional lines I set a seed value in order to ensure replicability of the results. And I define the number of bootstrapping samples. Normally I use 5,000. Now we get a confidence interval based on bootstrapping. So this confidence interval is robust against possible violations of the normality assumption and or the homoscedasticity assumption. And the same applies to the graph for the confidence interval. We got slightly different results, but in this example we can still see that the confidence interval does not fall completely within the equivalence bounds. However, when it comes to the tossed, we get exactly the same result that we got earlier. So the tossed procedure is not bootstrapped. So this result is still wrong if the normality or the homoscedasticity assumption are violated. So my recommendation is always use bootstrapping. For bootstrapping you need normally at least a sample size of 50, which we don't have in this example data set. Then I would report the bootstrap confidence interval. I would show in addition this graph, and based on the confidence interval as number and as a graph, I would decide whether I have an equivalent result or not. So I think it makes more sense to use the confidence interval approach than the tossed approach, because for the confidence interval approach, you can have this added robustness by using bootstrapping. If you want to know more about this way of doing equivalence tests and additional options of this R package, there's a paper by Alter and Counsell, 2 of the authors of this R package. You'll find the reference information in the video description. Thanks for watching and see you in the next video.